After understanding the first order difference equations and their methods of solution, now it's time for us to learn how we interpret their dynamic stability. So let's start with the dynamic stability of the first order difference equations. Primarily, there are two broad cases of their nature, because in the dynamic stability of first order difference equations there is an additional feature, and that is their ability to oscillate, or otherwise, that is, they do not oscillate. So this thing will be an additional feature in our analysis of the dynamic stability, whereas the matter of convergence will remain valid, because that is the most important thing when it comes to dynamic stability. However, oscillation or not is something that we will introduce in this analysis. So let's focus on that part of the time path that explains the dynamic stability, and you remember that it is the complementary function, and this is the value of the complementary function of the first order difference equations. So we take this as the starting point, and we assume that a is equal to 1 for the time being. We will also see the effect of a, but in the upcoming videos. But right now we are talking about the value a, and that we are considering equal to 1 for the sake of ease, because if we put a 1, then the complementary function reduces to this term, which is easier to interpret and is free of a. So this will enable us to observe the effect of b, and will keep a silent. So let's try to understand this b exponent t term. bt contains b, which further is composed of a. You know that bt has this term which is b, and b is also equal to minus a. So we should be mindful of the nature of b and a. This is the difference between the two. It is actually the base in the solution of the first order difference equations, whereas in the other situation where we are talking about a, it is the coefficient of the or in the first order difference equations, that is, a is here, whereas in the solution we have b, which in turn is equal to negative value of a. It has the ability to determine the dynamic stability, and a determines the formula that we use for yc. So it determines whether we are using the first formula, that is 1 plus a, or we are using c into t. So the selection of the formula for the solution is determined by this, whereas the value of b determines the dynamic stability. So now we consider various possibilities of this expression, that is b exponent t, and it can be either a positive value, zero value, negative value. So we consider b as a positive value greater than equal to 2, which is greater than 0, and then 0, and then less than 0. These are the three values that we assume, precisely speaking, -2, 0, and +2. If we use these values, we can say that these two are actually non-negative, because they are not negative. This one is, however, negative. So we start with 0, and it continues and goes till 10 and so on. If we put these values of t in this expression, for 2 raised to the power 0 will be equal to 1. Here 0 raised to the power 0 will be equal to 1, and here -2 raised to the power 0 will be equal to 1. So you can verify these calculations. 10 raised to the power, this is 2 actually, 2 raised to the power 10, so when we calculate 2 raised to the power 10, we expect this would be the answer. Here 0 raised to the power 10, here it will be -2 raised to the power 10. So these will be the answers. I have highlighted a few of them, 6 of them, 3 here and then 3 here. You can solve the remaining. So when we solve all of these, we observe a certain pattern, and the pattern is that the value is increasing here, it is remaining positive, the value remains 0 here, and the value changes its sign as well as increases in magnitude. So let's summarize all these findings here. Exponential growth was observed in the first column. There was no growth, neither decay in the second column, and there was exponential growth, however, with positive and negative signs. And in the first column there was only positive sign. We just saw this thing in the last slide. Positive sign, then no sign, and then alternative signs with exponential growth. So if we have positive sign throughout, the graph will remain in the first quadrant and it will remain smooth, as compared to the third column, where the graph will go into the fourth column as well, above and below. This is the first quadrant, this is the fourth quadrant, so it will adopt positive and negative values above and below. And there will be ups and downs because we will be entering from one quadrant to the other quadrant. Whereas this middle possibility will be a horizontal straight line because the value will remain 0. So there are three kinds of situations. In these two cases where the value of b was not negative, there were no oscillations. There was no movement above or below the axis. Whereas in this case, where b was negative, there is oscillation, that is movement above and below the x-axis. So this is the thing that we wanted to learn here, that there can be a possibility of having oscillations, which was not the case in the differential equations. This is an additional feature. So for all the possibilities of b where b is less than 0, we will have oscillations. To keep things simple, we are going to divide all of these cases into two categories. As in the very beginning of this topic, we said that we will discuss the non-oscillatory cases in this video. So only the oscillatory cases will be observed here. This thing is mentioned here that we will have oscillatory as well as non-oscillatory cases, out of which we'll be focusing on non-oscillatory in this certain video. The time path of first order difference equation is not just about convergence or divergence, it is also about their nature, that is if they are oscillatory or non-oscillatory. So now we are going to just label this set of possibilities in a more elaborated way on a number line. If we consider the value of b on this number line, we can say that if b is equal to 0, then definitely the actual value of b is 0, but its absolute value is also equal to 0. And then the other extreme is that the b value is positive, for example 2, actual value and absolute value. In this way we come a little below this, that is we come to b is equal to 1, its actual value and its absolute value. Then a little lower value would be 0.5, a decimal value. Its absolute version will also be the same. However, after this we have negative value of b, that is minus 1 over 2 or minus 0.5. This would be minus or negative value in its actual form, but its absolute form would be positive 1 over 2. That's where the absolute value would be different. Then if the value of b is minus 1, then its absolute value will be 1, and if the value of b is 2, its absolute value would be 2, and actually the value of b is minus 2. So these are the possible cases that we can have in the value of b. Can be before and after 0, and there would be positive values and there would be negative values. And now after summing all those 7 cases, we will focus on those cases that are non-oscillatory in nature. And we just learned that those cases where the value of b is non-negative, they will be non-oscillatory. So we will drop the 3 cases that have negative value, that is the 5th case, the 6th case and the 7th case. These are the cases that we will not study in this video. So we start with the first value, that is the first case, this one, and then the second one, the third one, and the fourth one. These are the four cases that we will study here. So this is the first region. The first case can be considered as the first region. This is the value of complementary function that we want to evaluate. So we will put various values of t, that is 0, 1, 2, 3, 4. When we put all these values, then we will have this situation that there is a positive base and its value, its power is also positive. So the result will also be a set of positive values, and then definitely it will be non-oscillatory, because oscillation happens when we have alternative signs. Here we will have positive signs throughout. So positive base is 2 in this case. We assume that the value of b is 2. So let's see how it will roll out. This is the case that region 1, that is b is greater than 1, absolute value will also be greater than 1, and we assume that value of b is 2. And when we put 0 here, we get 1. When we put 1, we get 2. When we put 3, then we get another value, 4 up to 4. So we can find out these values. Just to recall that we are putting t is equal to 0 in first case, 1, and then 2, and then 3, 4. All these values will be visible here, their answers. This is where t is equal to 0, and this is where t was equal to 4, and this is the value of b exponent t. And we are plotting b exponent t here, and you can see the graph will be a discrete graph. And in this discrete graph, the value starts from 1, it goes to 2, 3, 4, 8, 16. So this is 1, this is 2, this is 4, this is 8, and this is 16. So this is how the graph will look like. Now the nature of it is interpreted here. Primarily it is a divergent case, because you can see it's moving away from the equilibrium. So it's dynamically unstable. Secondly, it is non-oscillatory, because it is not moving above and below a certain point. It is moving in the same direction, that is upwards. Now let's consider the second region. And for the second region, we will consider that the value of b is coming down from greater than 2, it came down to 1. And its absolute version will also be equal to 1. So we are to find the value of bt to see the pattern of the deviation. So we put various values of t, that is 0, 1, 2, 3, and 4. So base is still positive, that is 1. So 1 raised to the power t, putting t is equal to 0 will give us 1. Putting t is equal to 1 will give us 1. And even in this case, let us solve this. B raised to the power t is what we want to solve, and instead of b I'll put 1, and instead of 4 t I will put 4. So it will be equal to 1. So no matter what is the exponent, the answer of this expression, that is 1 raised to the power t, will always be 1. So you can see that it is equal to 1, this value, and it is continuing to be at the same level no matter how the time is varying. So this time path is neither convergent nor divergent, because it is neither moving above nor it is moving below. So it's neither of those two cases. Then region 3 should consider the other possibility of value of b. You remember in the last we had b is equal to 1, so smaller values would be a value which is still positive but less than 1. That is some sort of fraction. And its absolute version will be less than 1. For example, if we consider b is equal to 1 over 2 or 0.5, it means that it is also 0.5. It is a positive value, a fraction or a decimal value between 0 and 1. And then you can do this experiment again. T is equal to 0, t is equal to 1, 2, 3, 4. And once you solve using base as 1 over 2, these will be the answers. So here you can put all these values. So you will get this array of values that you can plot in this graph, and when you plot it, this is 1. Let us label it. This is 1 over 2, this is 1 over 4, this is 1 over 8, and this is 1 over 16. So the values are converging towards equilibrium, so it is a dynamically stable case because there is convergence in it. So this was region number 3. Then there is region number 4, and in region 4 the same expression will be solved with various values of t from 0 to 4. However, the value of b will further decline. Previously it was a fraction, but now we are bringing it down to 0, and its absolute version will also be 0. And when we put it in this series of values, we say that b is equal to 0. So 0 raised to the power 0, 0 raised to the power 1, 0 raised to the power 2, 0 raised to the exponent or power, in this case 3, 0 raised to the power 4 will remain 0. So it means all of the values of the complementary function are 0. So here we have 0. This is 0 first, and this is second 0. This is third and fourth. So you see that there are zeros all around, and the YC curve is on the x-axis. YC is 0. It means that the time path is already on equilibrium. This is another finding that we have done here, because the deviation doesn't exist. So the time path is already at equilibrium. It is neither divergent nor convergent. In other words, we can call it pre-converged because it is already converged. There is no deviation. We will see this in the summary, and this is the summary of all these 4 possibilities that we have studied. And in all of these 4 possibilities, it was non-negative, the value of b, and a non-negative number when raised to any power generates a positive number, because it's a positive base, or it's a 0 base. Whenever we expand it using some power, it is going to give us a positive number, which gives rise to a graph which is time path in this case that will remain in the first quadrant. As you saw, all of these graphs, they were in the first quadrant. They were not entering into the fourth quadrant where the negative values exist. Therefore, it was non-oscillatory, no movement below and above x-axis. So the conclusion is that whenever b is non-negative, there will be non-oscillatory time path. And about convergence, the time path, the value of b in absolute terms should be less than 1, which was happening in this case. Here b was less than 1, its absolute value, it was 0, so there was already converged situation. Here the absolute value of b was less than 1, so we had convergence in this case. And we consider the second case. The second case was here. The value of absolute value of b was not less than was not less than 1. This is why, because it's equal to 1, should be less than 1. This is why there was no convergence, neither it was convergence nor divergence. It was somewhere in the middle. And the first case that we studied, its absolute value should be less than 1, which it was not, due to which there was no convergence and there was divergence. So the summary actually gives us a kind of pattern that we can remember for the sake of remembering the pattern of the time path of first order difference equations. Now we have a summary of all these cases. It is quite helpful. Region 1, region 2, region 3 and region 4. We have analyzed 4 regions. In region 1 b was 2, which was greater than 1, and in other words it was non-oscillatory because it was not less than 0. Again, b less than 0, non-oscillatory when it was 1. When b was a fraction, it was still not less than 0, so it was non-oscillatory. When b was 0, then it was still not less than 0, it was still not negative, therefore it was non-oscillatory. And in the second row we observe the convergence. When b was 2, it was absolute. In absolute terms it was not less than 1, it was greater than 1, so it was non-convergent or divergent case. When b its absolute value was equal to 1, then it was non-convergent. It means that it was neither converging nor diverging. You can pause the video and match these with the graphs that we have. And when the value of b was 1 over 2 and its absolute version was also 1 over 2, it was less than 1 in absolute terms, so it was convergent. And when the value of b in absolute terms was 0 in the region number 4, then its situation was convergent, and it was actually pre-converged. It was on x-axis. And then this part is about the absence of deviation, in which it was pre-converged because there was no deviation. So you can use this table or build it for the sake of better understanding. So we have summarized all these cases. Before it, we developed a summary and we developed some rules to understand the oscillation or convergence of the given situation, in which b can be equal to 0, b can be a fraction, a positive fraction, and then b can be equal to 1, or the highest value of b could be greater than 1. So these all cases were plotted on a number line, where only the non-oscillatory are explained in this video, and the last 3 oscillatory cases are yet to be explained, and they will be explained in the next video. And this is where we understood why oscillation and non-oscillation happens depending upon the value of b, and this was the difference of why a and b are slightly different and how they can be used for various interpretations. This was the main expression that determines the dynamic stability, which is the complementary function a b exponent t. So this was the set of non-oscillatory cases of the first order difference equation that determine the dynamic stability or lack of it in case of first order difference equations. In the next video we will develop the oscillatory cases, which will be 3 in number, and that will complete all 7 cases of dynamic stability of first order difference equations. Thank you.